Hello everyone, my name
Hello
is
everyone.
Charlotte and I'll be your host for today. Welcome and thank you for taking part in MDPI's webinar entitled Low Dimensional Materials for Optoelectronic Applications. This is the third webinar of this electronics series based on special issues from our journal of the same name. If you are interested in contributing to this topic, you can submit your research to any of the special issues that are linked to this webinar. Simply check the webinar's webpage for more information. I would like to remind everyone that this webinar is being recorded and the recording will be made available as soon as possible on the webinar's webpage. Today's session is also being live streamed on MDPI's YouTube channel, so hello to those of you watching us on there. Certificates of attendance are available upon request. To get yours, please send an email to electronics.webinar@mdpi.com. Certificates will be delivered to those who have registered and are watching on Zoom, not on YouTube. Thank you for your understanding. Today's webinar is chaired by Professor Elias Stathatos. Elias Stathatos graduated from the Physics Department in 1991 and received his PhD in Materials Science in 1999, both from the University of Terahertz in Greece. He was a visiting scholar at the University of Cincinnati in the USA in 2004. From 2005 to 2019, he was a faculty member at the Technological Educational Institute of Patras and is currently a professor at the University of Peloponnese. In the period 2008 to 2010, he was department head of the Electronical Engineering Department at the Technological Educational Institute of Patras. His research interests encompass different themes such as the conversion of solar into electrical energy using dye-sensitized quantum dot and perovskite solar cells employing nanostructured materials. Furthermore, Elias is also interested in the application of electrochromic nanocomposite materials in smart windows, as well as OLED and OFET devices and nanosensors in environmental applications. Thank you, Elias, for chairing today's webinar.
Thank you very much, Charlotte. So, hello to everyone joining us today, and I want to welcome you all to our today's session with the title, but first, just to share my screen, please. Today's session with the title, Low Dimensional Materials for Optoelectronic Applications, supported by Electronics Journal and especially the microelectronics and optoelectronics, which is focused on the fabrication of electronic, photonic, bioelectronic, electromechanics, and fluidic devices and systems. And of course, there are applications in the broad areas of electronics, photonics, energy, and the environment section. So, I'm Professor Elias Stathatos from University of Peloponnese. I'm today's chairperson of our webinar. Today, we have two distinguished presenters to talk about the research advances in the field of low-dimensional materials and their applications, Dr. Xiao and Dr. Meziani. Before I introduce today's distinguished speakers separately, I would like to give a short introduction to low-dimensional materials in general. So, low-dimensional, including two-dimensional, three-dimensional, one-dimensional, and zero-dimensional semiconductor materials have great potential in electronic, optoelectronic applications due to their unique structure and characteristics. At present, 1D nanomaterials, including nanowires, nanorods, nanotubes, and so on, have been widely studied. The high specific surface area and small diameter make them have many unique and excellent properties. Common zero-dimensional nanomaterials include nanoclusters, nanoparticles, and quantum dots. A cluster generally refers to a stable combination of several to hundreds of atoms, molecules, or ions formed by physical and chemical bonding. Changes in spatial structure and morphology make zero-dimensional nanoclusters exhibit versatility in physical and chemical properties. Nanoparticles are larger granular materials than clusters and range in size from 1 to 100 nanometers. Quantum dots are a class of nanoclusters that they behave like atoms. Size effects cause changes in the chemical and physical properties of quantum dots. Moving now to the topic of our invited speakers, the successful preparation of graphene has opened up a wave of two-dimensional material research. Due to their unique properties, 2D materials have demonstrated their promising potential for application in many ways over bulk materials such as optoelectronic applications. Graphene as 2D material has many excellent properties such as superior electrical properties due to ultra-high electromobility, excellent mechanical properties, and excellent light transmission and thermal conductivity. In terms of dimensions, the 2D material is a layered structure and the movement of the particles is limited in one dimension. The atoms at the in plane are bonded by covalent bonds and the layers are bonded by van der Waals forces. 2D materials achieve an ultra-thin thickness at the atomic level, which is distinguished from ordinary conventional materials in dimension. Correspondingly, one-dimensional materials with 2D motion constraints and zero-dimensional materials with finite three-dimensional motion have also been extensively studied. From an application point of view, the unique electrical and optical properties of low-dimensional materials make them widely used in nanoelectronics and optoelectronics. Many 2D, such as transition metal dihalogens and black phosphorus, and 1D, such as nanowires, materials have demonstrated superior performance in field effect transistors, photodetectors, and some flexible devices. In the application of photodetectors, the variety of low-dimensional materials and properties enable wide spectrum detection from ultraviolet to infrared, which provide a potential option for photodetectors under various conditions. For flexible electronic devices, high performance and mechanical stability are two important features. Finally, low-dimensional materials offer unparalleled advantages in flexible devices. But I think it's time now just to give floor to our first distinguished speaker, which is Dr. Sanshui Xiao, which just give me a few seconds just to introduce our speaker. Dr. Xiao obtained his PhD degree at Zhejiang University in 2004, and he's now an associate professor at the Technical University of Denmark. His current research interests mainly focus on the exploration of fundamental physics of light-matter interactions and the development of 2D materials-based optoelectronic devices. He has published more than 120 journal papers with a total citation score of 2,000 citations and an H index of 33. He has co-organized several sessions at Peers and AME and EMN conferences and obtained the European Optics Prize from the European Optical Society in 2008. So please, Dr. Xiao, I give the floor to you just to listen to your very interesting lecture now. Thank you very much.
Thanks, Professor Elias. I would like to thank your invitation for giving this webinar. So actually, personally, I also attend lots of webinar, which kind of invite friendly. You don't need to travel, which generates lots of CO2, and also yeah, it's kind of interesting. And I would like to say, because this kind of, I would like to point out the data communication. Nowadays, lots of needed for this data communication. There is strong needed for how to save energy consumption as well as increase the bandwidth. For long range communications, we always use this fiber because fiber provide a large bandwidth. And also for the database, actually, we used fiber solution a lot to transmit information between different components. So today I would like to discuss about how to use optics for interconnect on the chip level. So let me just start. Oh yeah, that works. So first I will give a brief introduction of Technical University of Denmark. So we are located in Copenhagen, a capital of Denmark. It's like 10 kilometers away from the center of the city. Actually, this university was founded by H.C. Ørsted, who discovered the connection between the current and the magnetism. So this university is kind of small university. We have around 12,000 students, but we have 5,000 staff, including PhD students. So we have a very special ratio between the staff and the students. And yeah, this is our actual main campus at Lumby. And recently we have merged a number of national laboratories in Denmark. Therefore, we have like 5 or 6 campuses in Denmark. And this is actually our nanofabrication clean room facility. It's a national nanofabrication facility in Denmark. And this is actually our new building for photonics engineering. And we have a state-of-art electron microscope center, which is able to check the materials properties. And we also do this electron loss spectrum at the DTU CERN. We have a very advanced E-beam lithography and to make some nanostructure. So yes, so as I previously mentioned, our main kind of research topics is to how to reduce the energy consumption and increase the capacity for the data communication, especially at the level on the chip. So when we talk about the longer wavelengths, this is somehow the optical connect for the data center. You can see lots of fiber are used to transmit data between different devices. But actually on the chip level, still we're using the electro interconnects. So it turns out that we have 50% of power consumption responsible for this electro contact. And also the bandwidth somehow is limited for this electro contact. Therefore, actually, people have proposed to use optical contact in order to overcome the bandwidth and decrease the energy consumption. So silicon-based optical contact has been proposed for probably more than 20 years. So basic idea is that we will use optics to transmit information from one device to another devices, and then use electronics to do their calculations, to do the information process. So therefore, we are able to somehow, so first, decrease energy consumption, another is to increase the speed. So of course, if you want to somehow, make like a silicon-based optical interconnector, you have to provide lots of high-performance devices, including lasers, waveguide, modulators, and photodetector, etc. So our research is to how to use these 2D materials to make some silicon-based device with high performance. So 2D materials actually, actually this somehow we start from the graphene, which was discovered in 2004, and later actually the graphene, the topic was given in Nobel Prize in 2010. Actually, this is kind of a paper from physics department at DTU Physics. They actually did some ab initio calculation to predict that at least more than 2,500 2D materials. And of course, we still have some challenge to fabricate or synthesize these 2D materials, but it gives lots of opportunity to study 2D materials. And there is another topic is that we can stacking these different 2D materials on top of each other, such as like the Lego, which also is a very famous company from Denmark. And also when we stacking, we can twist the angle between different layers. This also gives lots of kind of opportunities for tune or control the optical and electronic properties. So this figure just show kind of two examples. One is we can realize superconductor in two bilayer graphene with magic angles. And also for this kind of transition metal diacrylonized, we can realize to localize chip the extron, where they can, by use of Morley pattern. Actually, there is a kind of very interesting topics where we can somehow realize arrays of quantum single source by use of this twist angle technique. So of course, we are working on like optics electronic properties. So we are mainly focused on how we can use 2D materials to enhance light matter engagement and also to make some novel devices. So actually 2D materials can cover the range from visible to terahertz windows. For example, hexagonal by HBN is kind of insulators where we can use this material as a protection layers. And the transition metal diacrylonized, this material has a very interesting property. It has a very strong binding energy, and also somehow the band gap become directly if we decrease multi-layer to a single layer. Therefore, actually, we can use this transition metal diacrylonized to make some light source, even for the laser source. So graphene, it's kind of a semiconductor. It can work from visible to terahertz. So actually, in this talk, I will mainly focus on graphene-based optical devices. So here, left panel, I just show some of the example of this 2D materials where we can use for this novel applications. The first example is that we can use this transition metal diacrylonized to make some laser devices. And this part is that actually we are using this HBN, the insulator, then use somehow oxygen plasma to artificially generate some defect. So actually, it turns out we can realize a single photon source at room temperature by use of defect in HBN. And this is just an example of how we use this graphene to make some modulator. So I will discuss this kind of topic in the later point. So of course, this graphene has many unique properties, also as mentioned by Professor Elias, and also, the graphene flagship, it somehow is allowed €1 billion for the research of topics. So if we look at the band structure of graphene, you can see there is a Dirac point, meaning that the density of state at this level is 0. So you can either somehow change the Fermi level in graphene, either by electro tuning or chemical doping. So, and also this dispersion is kind of linear dispersion, meaning that effective mass of the carrier is 0. Therefore, in graphene, it has a very speed, carrier transitions. And also, this is because of semi-metal, it can absorb all kind of light. So graphene can behave as a broadband absorption. So below, I just show a kind of illustration of the device that I will talk about later. So if the energy of the light is more than 2 times Fermi level, then this light becomes transparent. So when we tune the Fermi level and the energy of the light is larger than 2 times Fermi level, then this electron as a photon will be absorbed by the graphene. So basically, you can tune the Fermi level of graphene to control whether light will be absorbed or transparent to the graphene. This is somehow the basic kind of mechanism for making these modulated devices. So I will give a number of kind of device we have recently worked on. So first is like graphene silicon-based electro-optical modulators. So these are the 2 kind of first kind of devices where they integrate graphene on top of silicon waveguide. So I think here the waveguide size are a few hundred nanometers, and they just chemical transfer graphene on top of silicon waveguide. Of course, between these 2 materials, there is a layer, aluminum oxide, which acts as a capacitor. Then afterwards, they will make some contact to the graphene and to the silicon in order to tune the Fermi level of graphene. So this paper is also based on silicon devices, but because silicon has a very high refractive index, if we think of the optical mode, this mode is somehow localized within the waveguide. When we put graphene on top of the waveguide, the interaction between the graphene and the optical mode is kind of relatively weak. So our idea is that how to increase the interaction between the graphene and optical mode in the waveguide. So here, actually, we propose a device. We have a silicon waveguide here. Then there is a micro ring resonator, which is side coupled to the silicon waveguide. Actually, on the top of this ring resonator, we have this graphene. We transfer graphene on top of silicon ring resonator. Then in the end, we made this contact to the graphene and to the silicon substrate in order to tune the Fermi level of the graphene. So we shine the light, not shine. We somehow couple light from our fiber to silicon waveguide. Then, then some part of the light will be coupled by this ring resonator. Because this ring resonator has a very high quality factor, when the light is trapped within this ring resonator, the light will travel many times around the around these ring structures. If we put graphene on top of a ring resonator, you can consider that interaction between the graphene and the optical mode will significantly enhance because of the light is circulating many times within ring resonator. So this is actually our kind of a basic idea to increase the interaction between the graphene and the optical mode in the waveguide by use of resonant mechanism. So here actually the right is just show our SEM pictures. So again, actually, if we want to fabricate these kind of devices, we have to rely on E-beam lithography. This all size of the silicon waveguide is on a few hundred nanometers. And I want to emphasize here, actually, we use the chemical wet transfer method, transfer the CVD growth to graphene on top of our devices. We did not use this mechanical exfoliation method. So the main idea is that we want to have some mass production of a device, right? Because normally the size from the mechanical exfoliation is very small. We cannot make many devices. But by use of CVD growth graphene, then we are able to make wafer scale devices. So of course, there's still some challenge when we do this chemical transfer. Sometimes, as a graphene will be cracked or broken. But yeah, I think there are lots of progress regarding this wafer scale mass production for this optical electronic devices. Again, as I mentioned, this waveguide is very small. So how to couple light from our light to our devices? So actually, this black area is kind of waveguide. You can consider it's only a few hundred nanometers. Actually, we are using a tape structure. Then this part actually is kind of a grating. So here actually the grating was designed as like a photon crystal grating. You can see it's a grating structure, but each period there are lots of holes. So actually we just optimize the kind of structure in order to increase the coupling efficiency from a fiber, a single mode fiber, to our silicon waveguide. Of course, there are lots of kind of optimization, and our conclusion is that actually we can use this kind of grating technique to couple light efficiently from the fiber to our waveguide, and the coupling loss is like minus 1.7 dB from the fiber to a waveguide. Again, actually, this is actually our ring resonator. This blue area is kind of graphene. Then we made the contact to tune the Fermi level in the graphene. Then actually, again, we will use this grating coupler to couple light from our waveguide to spectrometers. So again, actually, because the ring resonator is third coupled to the waveguide. Actually, there are lots of studies in order to how to increase the kind of the modulation depth, also the decrease in section loss. So actually, this part is kind of numerical study to optical design structure where provide high modulation depth and to increase also the in section loss performance. So actually, by use of E-beam, actually we can make any kind of structure you want. If we look at this kind of section, this is a ring resonator. So actually here only like 25% of the ring is covered by a graphene. And here is like 50% of the ring is covered graphene. This is also 75. The purpose of that is to kind of try to increase the modulation depth and also increase the bandwidth. Because as I mentioned, actually, this kind of device is mainly, relying on the resonant mechanism. So only the light where the resonance, this part can be like enhanced for this modulation depth. For the light, which is away the resonance, actually the light will be direct pass through the waveguide. So therefore, the bandwidth somehow is limited. So here, for example, if we look at this structure, this is the bias is a voltage, right? We can change the voltage, and eventually you can, this is the modulation depth. Then we can change, we can have a very high modulation depth, okay, for these devices. But you can see the bandwidth is very narrow. It's only at 1.55. This because of this kind of resonant features. If we made a kind of large size of a graphene coverage, then you can see the modulation depth decrease a bit, but the bandwidth increase. So there is kind of a trade back between the modulation depth and somehow bandwidth. Then we can further, optimize this bandwidth as well as this kind of modulation depth. But actually, in this device, of course, our aim is to make fast modulation by use of graphene. So actually, in the end, and the speed for this type of device is not so fast as we expect. So here, actually, we are using another kind of concept to make some waveguide. Actually, we are using this metal as a materials for the waveguide. Of course, there are lots of topics regarding the metal because the metal supports some plasma, the oscillation of electrons. This oscillation of electrons, if, for example, if we look at this kind of, if we go to the church, you will see lots of color on the window. This is due to the plasma resonance from different sides of metal particles. There are also a very hot topics regarding quantum plasmonics, especially when two metallic nanostructure are close enough only to like 3 or 4 nanometers. There will be lots of optical response that you cannot explain by classical theory. So actually there is a kind of very hot topics on quantum plasmonics, where we need to take the quantum effect when this metal piece are close enough. So for the optical interconnects or optical devices, actually we can use metal to make some waveguide. Compare the silicon waveguide, actually we can somehow really focus the waveguide mode on the diffraction limit, under diffraction limit. So of course, silicon waveguide, you can also make a very small waveguide, but if we consider the effective mode size is always on the order of wavelengths. But the plasmonic waveguide, you can make a small waveguide where the mode is very focused below the diffraction limit. So actually, we will use this kind of plasmonic waveguide for making some devices which is integrated with 2D materials. So here is that, we just propose, this is kind of a cross-section of waveguide. So this waveguide structure is kind of simple. We have a metal, this metal film. Then we cut a slot. Then this is kind of metallic slot waveguide. This is just a cross-section of waveguide. If we look at the optical mode, you can see this mode is very localized within this gap. And here I think the size of the gap or the width of the gap is only 100 nanometer. And also here, actually in this device, actually we have 2 layers of graphene. So here actually, in order to increase, modulation depth, and we made 2 contact, one to one graphene, another contact to another graphene. And in between, again, we have this aluminum oxide layer, which acts as a capacity. So here, actually, by applying the voltage to the 2 layers of graphene, we just change the optical property of graphene. When the graphene is on top of the waveguide, eventually we just tune the optical transmission for this light through this slot waveguide. But again, there is kind of a critical issue how to couple light from our fiber to a 10 nanometer wide plasmonic waveguide. So actually here we propose a kind of, silicon taped structure to couple light from a fiber to this plasma waveguide. So again, actually we are using this photon crystal coupling to couple light firstly from fiber to silicon waveguide, then use this silicon tape structure to couple light from silicon waveguide to plasmonic waveguide. So this actually is our SM picture. You can clearly see there are two layers of graphene on top of a metallic slot waveguide. This part is a silicon taped waveguide. But actually in this device, actually the metal contact is a bit far away from waveguide because this contact are made by a lithography, not by E-beam lithography, just by optical photolithography. So I mean the distance is kind of a 5 nanometer. But this metal actually has some intrinsic ohmic loss. When we choose the metal as a material for the waveguide, of course we can confine the light within very small area, but we need to pay price that the metal has some loss. So actually, if we look at our waveguide without the graphene, just plasmonic or metallic slot waveguide, the loss is like 0.25 dB per micrometer. When we have the graphene, it increased to 0.68 dB per meter. So here actually it shows like transmission as a function of the voltage. We apply the voltage to the two-layer graphene to check how the transmission changes. This we also call it the modulation depth. Within a given like a kind of voltage, we will see the modulation depth. So if we compare the silicon-based modulation devices, actually here the modulation depth is like 3 times larger than the silicon devices. Again, because this device is based on waveguide. So in principle, the bandwidth is very large. Compare the ring resonator that previously discussed. So this is I will see another example where we can use this graphene and plasmonic waveguide for photo detecting applications. So these are some previous work on this graphene photo detector. Here, actually, this is kind of top emulations. Okay, and they are using different metal contact in order to separate carrier generated by absorption in graphene. And these three are based on silicon, waveguide. Again, as I mentioned, that we want to use this plasmonic waveguide in order to improve the performance for photo detecting, and also we want to mainly to focus on how to increase the speed. So if we look at the device, this is kind of similar to the configuration for the modulators. So the main difference is that you can see this is also a slot waveguide. Okay, we have metal, then this is a gap. Okay, this is kind of a plasmonic mode or optical mode for this slot waveguide. And actually, we have a graphene, a single layer graphene below this plasmonic waveguide. Now, when the light is propagating through the waveguide, by the absorption of the graphene, then the carrier electron hole pair will be generated. If we have a BIOS or built-in kind of electric field, then electron hole can be separate in the end, resulting in a current. So here, compare the silicon-based photodetector. So here, this metal behave as materials for the waveguide as well as for the contact. So our kind of hypothesis is that due to this subwave light confinement, we can have very strong light absorption in the graphene. And also due to this narrow slot, when the carrier is generated within the graphene layer, then it can easily separate, resulting in the current. So we expect that it will be very fast carrier transition for these devices. And also here, actually, we are using this unsymmetry configuration. Actually, without BIOS, we can still see this current. Okay, this device, we are using the same kind of coupling mechanism to couple light from fiber to slot waveguide by use of photon grating as well as silicon-based taped structures. So again, actually, yeah, this slide show, because this is only like a 100 nanometer gap, and our silicon waveguide, actually the size is 600 nanometer. There's still some kind of challenge to how to efficiently couple light from silicon to this slot waveguide. Actually, we did some, kind of design or optimization in order to increase the coupling efficiency. Actually, here coupling efficiency is like, yeah, we can achieve like a 1 dB. I think coupling efficiency is still very high, even. But of course, it will rely on, a good alignment between the silicon waveguide and the slot waveguide. If these two waveguides are kind of misalignment, then it will decrease the coupling efficiency. Yeah, this is a SM picture, and also, when we do this chemical transfer, we also care about the quality of the graphene after wet transfer. So actually, we are using this Raman spectrum to check the quality of graphene after this wet transfer process. So here, actually, because actually, this plasma waveguide has a high loss. Actually, we actually optimize our nanofarad process in order to decrease the loss for the plasmonic waveguide. Actually, the loss of this type of waveguide is very small. And also, this is like 0.8 for this kind of plasmonic waveguide per, I think, 0.5 dB per micrometer. Is this, yeah, of course, I think there are two kinds of key features for these photodetect devices. One is responsivity, another is speed. This just show responsivity for different BIOS, and we achieve very high kind of like responsivity for giving voltage. And actually, we made a number of devices with different lengths for the plasmonic waveguide. Yeah, of course, in order to measure the speed or the bandwidth of photodetector, in this kind of, we have developed 3 different ways to measure the bandwidth, because some method somehow are limited by our devices. For example, our vector network has a maximum speed of 40 gigahertz, and then I think for this blue line actually was made by our BNA, where the bandwidth to 40. Then we develop a different type of method. Actually, it shows actually the bandwidth. If we talk about 3 dB, actually here is like a 1.5 dB. The bandwidth is around 110 gigahertz. And we cannot measure the speed above 110 because of the limitation of devices. So here actually, we also made some comparison between our device here, the red line, and with silicon-based devices. So first, you can see this is a type of graphene was used for different devices. So we are aiming for this CVD growth graphene because it has some opportunity for mass production. We don't want to use this accelerated graphene. And this is our speed. You can see is kind of higher than the result from other papers. And this is efficiency. Okay. Yeah, I think let's see. I'm not sure I spent half an hour, but I will just give a kind of small summary. Actually, we rely on the special property of graphene to make some devices. This device has some, performance which is better than the conventional silicon-based devices, and also 2D devices give some new opportunity. For example, making some lasing for the silicon platform, because silicon is a kind of indirect bandgap. It's difficult to make a laser devices, but 2D materials, for example, transition metal diagonals, we can make some laser for silicon optical interconnect. And this kind of photo detector and modulator will also beneficial for silicon-based optical interconnect devices. And the last, actually, I will give acknowledge, especially to Yun Hong, who is kind of main driver of these topics. And we have lots of collaboration from DTU colleagues and actually some university in China. And this part of our activity mainly funded by, we have a center of nanostructured graphene, and another excellent center is the Center for Silicon Photonics for Optical Communications. Both are funded by our Danish National Research Foundations, and we have also other foundation support our activities. Thanks for your attention.
Thank you very much, Dr. Xiao. I think that we have some time at the end of both lectures for some questions. So we have to go now to the next lecture. Let me introduce the speaker, please. Dr. Yahya Meziani is currently working as an associate professor at the Department of Applied Physics in Salamanca University in Spain. He was working as a researcher for Tohoku University, Japan, and in Montpellier University in France also. Dr. Meziani has been conducting research on the quantum Hall effect phenomenon and its application for the conversion of the ohm unit. His research focuses on the development of new electronic devices that can emit and or detect terahertz radiation at room temperature. He's author and co-author of more than 90 scientific publications, and his work is recognized by NH Index 19 in Web of Science. So, Dr. Meziani, we are nice to hear you. Thank you very much for being with us.
Thank you, Professor Elias. Thanks for the introduction. First of all, I would like to thank the organizer, and especially MDPI, for this invitation. It is a great pleasure to share with you our new results, and also to be part of this third webinar. So thanks, and thanks also, Professor Elias, for the introduction, and for the introduction also for the low-dimensional material that you made, as well as the Professor Sanshui. So today I would like to share with you some results or new results that we obtained here in our university about the development of 2D material-based devices and also their use for the Terahertz technology. So as you can see that there is two parts of my talk, is the 2D materials, how we fabricate these devices, and also how we use them for terahertz imaging or and inspection of hidden objects. So, okay, I belong to nanotechnology group at the Salamanca University. Salamanca University just is one of the oldest university in Europe, and I think is the oldest university in Spain. It was built in 1218. And we are like, I mean, about 200 kilometers from Madrid. You can see from the map here, and about 100 kilometers to Portugal. So there's a lot of history in this city. One of them is the Plaza Mayor that was constructed in 1726, and is one of the famous plazas here in Spain. Also, what you can see in this part here, front of the Salamanca, this is the, I mean, this is the headquarters of the university with this front side, and this have specific meaning for the university. Inside this building, you have also one of the oldest library with very old books that was built in 1254. So our building, we are working in this building. So the university have different part. So, and our investigation part is inside this building, which is very close to the cathedral of the university, the Plaza Mayor is around here, and the USAL headquarters is also around here. I hope that in the future you can have the time to visit the city for conference or for fun. Okay, so I come back to the outline of my talk. I first will show the motivation where I will introduce the 2D materials and also the terahertz technology. Then I will move to the method that we are using to fabricate this called asymmetric dual grating gate graphene-based field effect transistors. And the third party, I'm going to show some results that we obtained on the detection of radiation at 0.15 and also 0.3 terahertz, and how we can use these devices at room temperature to make some inspection of a hidden object. Then I will conclude my talk. Okay, so the motivation, the use of the low dimension material for the new era for optoelectronic application, that it was very nicely introduced by both professors in the first talk. And we are especially interested in 2D materials, the part of the two-dimensional materials. So this is started really in 2004, as it was said before, with the fabrication of the first monolayer graphene by professors from Manchester, Professor Novoslov and also Professor James, that later they obtained the Nobel Prize in 2010. So the story starts from there. It was possible to fabricate a single atomic layer of carbon. This is mainly the most important things. And then, things are going on in the future and has a lot of development, and it depends on what type of material you are looking, what type of 2D material you are looking. When you can choose one or other, depending on your applications. So from the semi-metal, where there is graphene, here you have the graphene as an example. From the metal, you have also, you can use titanium disulfide. Semiconductor, you have the transition metal chalcogenide. Insulator is the hexagonal boron nitride. Both of these were introduced before. And also you have superconductor and topological insulator are also very famous. They show very novel properties, for both fundamental physics and also for the applications. In our case, we are interested in mainly graphene material. because we can fabricate this type of sheet of graphene, and also hexagonal boron nitride. The idea is, since the hexagonal boron nitride is dielectric, is insulator, so it's belonging to this part, and the graphene is belonging to this part. So the idea is to put the graphene between two layers of hexagonal boron nitride. This is increase a lot their quality, and also avoid any contamination of the graphene sheet, as I will explain later. So the graphene, I mean, has a lot of properties for different type of application, but the graphene is mainly a single layer of carbon atoms. Okay, and this, I mean, organized as like honeycomb structures, as I saw here. This single layer is transparent to visible light. I mean, from this paper, you can see that the transparency of one monolayer of graphene is about 97.7%. From this figure here, I mean, you can see that this is flakes of graphene that were obtained by mechanical exfoliation methods, where we can distinguish here the monolayer, the bilayer, and more than 3 layers here. So just from the transparency, you can say, if with some experience, you can say if you are dealing with the monolayer or bilayer or more than 1 layers. So this is like the first step of the identification of the graphene sheet. Why we are interested in graphene? I mean, mainly this is summarized here in this figure, where we show here the electron mobility, which is in centimeters squared per volt second, as function of the band gap for different type of material. And if you can see the graphene, if you can see the graphene shows very high electron mobility. This is the most interesting properties for development of electronic device, for optoelectronic or for other type of applications. You can also see some bilayer graphene shows also very high mobility, graphene nanoribbon. And you can compare with, for example, here, you can see the silicon bulk, most the transistors. You can see the 3,5, also some of the 3,5 materials show some high mobility, like gallium arsenide, like indium gallium arsenide. But still the graphene is one of the, I mean, shows one of the highest mobility that can reach, I show here, about 500,000 centimeters squared per volt second, and also has a band gap of around 0 electron volts for the case of one sheet, of one layer of graphene. So this is the most interesting properties for us to develop or to use this type of material for electronics. Okay, so the graphene, I mean, here you said the energy diagram could have different behavior. For mono layer of graphene, there is no band gap. Here is the conduction band, valence band, and how you have in the between you have the Fermi level. So you can have conduction by both electrons and also by holes, depending on the bias. In the case of unbiased bilayer graphene, that can show some, or biased bilayer that can show some opening gap that is very useful for absorption of light. And absorption of light could also occur here. I mean, that electrons could go from this band to the other band with low energy, and can easily travel from here to from this level to the next one. So in summary, what we have, the high carrier mobility and also velocity of this carrier that is higher than 100,000 centimeters squared per volt second at room temperature, do have 0 energy gap or some small opening, which is very helpful or very useful for the absorption and emission of low energy photons, for both, I mean, for detection or for lasing. And to have also high quantum efficiency of light matter interaction because of this. Now, I mean, it is mainly used graphene fabricated by CVD method or by epitaxial method that is now used for different type of application, like the electrode for the batteries, sensors, or for low-cost water desalination and among other applications. The other 2D material that we are interested in is the hexagonal boron nitride. And the hexagonal boron nitride shows his structure is similar to the carbon lattice, which means that it is much more easier that we can put a graphene layer on HBN, and this avoid, for example, contamination. The HBN come like in powders in this, as I show here in this figure, and one exists in different crystalline form, and one of the most stable one is the hexagonal one. So this is why we use this hexagonal boron nitride. The gap of the hexagonal boron is about 5 electron volts, which is a good dielectric with the refractive index of about 1.8. It is good dielectric, good insulator for development of graphene field effect transistor. What I show here is a flake of hexagonal boron nitride obtained also by mechanical exfoliation. So we will obtain graphene by exfoliation, we will obtain HBN by exfoliation as well, and then the idea is to combine, to sandwich this graphene sheet between 2 layers of HBN. Okay. So this is the part of the 2D material. The other part, which is the Terahertz technology. I mean, the Terahertz technology is the terahertz gap, which is the frequency between 0.1 to 10 terahertz. As we say, it is the final unexplored area of electromagnetic spectrum that is left without, I mean, within the last 10 or 15 years, there was a lot of investigation to fill this area. And mainly, as I show here in this first figure, I mean, the terahertz gap is between the 0.1 to 10 terahertz, is included between the microwave range, where we have the satellite broadcasting communication, and also for the optic side or photonic side, which is the infrared, where we found the optical communications. But between, it was very difficult to develop devices or instruments that can work with this in this range. Why? I mean, mainly because here in this part we are working with electronics. And electronics is limited by the relaxation time or of the device. And when we enter to this, the terahertz gap, we reach the limits, so we cannot go further. The carrier cannot go further. From the other side, we are limited of the energy, because here the terahertz gap, I mean, as I show here, 1 terahertz is 4 milli-electron volts. So far below the thermal energy, which is about 26 milli-electron volts. So this is why it was very difficult to develop devices within this range. And you can see also here from this figure where I showed the output power of different type of lasers as function of the frequency. You can see from the electronic part, we can, I mean, use the impact diode, the GaN diode, the UTC-BT diode, the resonant tunneling diode. But when we go inside the terahertz gap, the emitting power is very low because of this limitation of transit time of carrier, which is less than 1 picosecond. And from the other part of the photonics, you can show the 3-5 lasers, like the quantum cascade laser, the p-germanium laser, the free electron laser. Yes, this gives very high power, but this is very expensive and this is very huge system installation. This is like only we have 2 or 3 in Europe, if I remember. And as I said before, it's mainly limited by the energy, 4 milli-electron volt at 1 terahertz. Okay. In terms of applications, I mean, since this is low energy that can go through to different type of material, so we can do inspection. As I stated here, most of non-metallic material are transparent 2 terahertz radiations. So we can penetrate deeper into material than visible or infrared. So this is very useful, very helpful for terahertz inspection and imaging. In terms of communication, I mean, we are talking about more than 100 gigahertz of carrier oscillations, which is very high frequency. So we are now, you can see we are now entering in the in terms of communication, the generation 6, where the transmission rate, it will be more than 100 gigabit per second. So we are entering in the terahertz beam. This will allow us to reach gigabit wireless communication with a very high, ultra high transmission rate. And in the term of spectroscopy, since it is very low energy, so we can excite very specific mode of vibration or rotation of molecule, which means that each material could have his own fingerprint within this range. Here I show just, I forgot to put to put here the reference, but here is just, I mean, standard measurement of some explosive like RD, TNT, PTN, where they show different behavior within the range of 0.5 to about 3 terahertz. Okay, and we are, in our case, I mean, we are using this called plasmons or plasma wave oscillation. It was also very well introduced by Professor Sanshui in the first talk. But in this case, it was, I mean, this is the plasmons in the metal. What we are trying to make is the oscillation of the plasmons in the channel of 2D in semiconductor like. So it was, I mean, first introduced in 1993 by these two professors, Diakonov and Chur, where they showed that the plasma, I mean, this was known well before, the plasma frequency in the 3D system do not depend on the dimension, depend only on the electron density, you can see here. So whatever I mean, you couldn't change the plasma frequency with the dimension. For this type of ungated 2D systems, the plasma frequency, yes, show dependence of the wave vector, which is inversely proportional to the length of the system. Here you have like the raised square root of dependence on the K. But when we go to the gated 2D system, which is the case of the transistors, we have a gate, you have a channel. This is the separation of the dielectric, D, separation between the channel, the metal, and the channel. In this case, the plasma frequency is linear with the wave vector K. And this term is mentioned here as the plasma wave velocity. In this condition, if the Kd is the mentioned, I mean, D is the distance between this, K is inversely proportional to the length of this system. If we fulfill this condition, then we can tune the plasma frequency by the length of the device. Which means if we decrease the length of the device, we can reach higher frequency. We can go through the terahertz range. So this was the theory, I mean, the beginning of the story. And here just some analogy for the students that are around. I mean, we can make the analogy of the plasmons with the sound waves. So the plasma waves is the oscillation of electron density in the space, as it is shown here in this figure, which is the thesis of Professor Knapp from Montpellier University. And the sound waves, I mean, that you are making pressure of the air and the oscillation of the air that could, from the generation of the sound to our ear. Difference is mainly in the dimensions. Sound waves, I mean, we are talking about dimension about 100 centimeters to 1 meter. Plasma waves, we are talking about 0.1 to 1 microns. The speed of waves, of the sound waves, is about 300 meters per second. The speed of the plasmons is about 10 to 6 meters per second. For these two conditions, that gives us the frequency, which is the S divided by L. Which is, I mean, when we are talking about sound waves, we have frequency from 0.3 to about 3 kilohertz. with this dimension. But if we're taking a transistor with this dimension, we can tune the frequency from 1 to 10 terahertz. Okay, so this is what tells us the theory. Then later on was a lot of work. I mean, since the first observation in 2002, where we can distinguish two modes of or two regimes of operation of our transistor. The first one, which is the resonant behavior, which in this case, according to this formula, W, which is S multiplied by K, we can reach something similar to this, where the frequency is function of the gate length and also of the gate voltage. So which means if we change the gate voltage, we can change the frequency that we are detecting, which is mean we can have like a resonant detection. On the other side, but in this case, we should have like the oscillation of the plasmons in all the channel. Okay. But we have observed that in a lot of experiments, it was not the case. But what we have observed is some broadband detection. I mean, we excite with our device with the terahertz radiation, and we got a signal. And the signal is is the same if we excite with 200 gigahertz with 1 terahertz. And this was explained as like we are not having a plasmon that are oscillating inside the channel, but we have like dampened plasmons, which plasmon is generated in one side, but didn't reach the other side of the channel. And in this case, we talk about, we introduce what is the effective length of the oscillation. And to have resonant behavior, the effective length should be higher than the gate length. Otherwise, we will always have this broad band detection. So just the state of the art, the first theory was starting in 1993 with this paper of Diakonov and Chur, followed in 2002. Like 10 years later, the first observation of non-resonant detection by using gallium arsenide or gallium nitride field effect transistor excited at 0.6 terahertz. Between 2002 to 2012, there's a lot of advancement because there's a lot of use of CMOS devices with gallium arsenide devices, indium gallium arsenide devices that show really detection of terahertz radiation by using this type of transistors. And in 2012, it was the first observation of detection by using graphene field effect transistors. In this case, graphene was deposited on silicon dioxide, also on silicon substrate, and with this type of antennas, and they demonstrate some detection with some responsivity under excitation of 0.3 terahertz. 2004, other type of integrated antenna by using this time CVD graphene shows detection of 600 gigahertz or 0.6 terahertz detection. In our case, we also demonstrate in 2014 very high responsivity and also very low noise equivalent power, which reached 20 kilovolts per watt. In this case, we were using like special. We were not using antennas. We were using specific structure, which is asymmetric dual grating gate devices. In this case, we were using like indium gallium arsenide devices. And more recently, a resonant behavior has been observed at 10 Kelvin. You can see here at 10 Kelvin, a resonant behavior was observed by using bilayer graphene with integrated both antenna and also the silicon lenses. Okay, so this is mainly the motivation. Now we are going to introduce a little bit the graphene-based devices. So here, as I said before, we have our graphene sheet on the silicon substrate, the top hexagonal boron nitride and the bottom hexagonal boron nitride. Here we have like tips with like polymer, which will help us first to take the top HBN from this substrate, then deposit it on this graphene, and then the next step, taking both and make the deposition on the bottom HBN. In this case, you can see that we are not having any touch with the graphene layer. This is maintain very high quality of graphene. So this is, I mean, like small animation. Take the first top HBN, deposit here, and take both, and then make the deposition on the last sheet. Okay, and then finally you will have bottom HBN, graphene, and the top HBN, and then we go to the next step where we make the top gate and also the drain and source contacts. So the method we are using to make this is called the hot pickup technique, because we are hitting the substrate. Here you can see the hot plate. This is the substrate with HBN or with graphene, and this is here you can see the glass with the polymer that we are using to pick and deposit the graphene layer. Okay, for each step, we make like this Raman spectroscopy. I mean, to verify that first to verify that we have only one layer of graphene or two layers, depending on the device that we are trying to make, and then finally to characterize the HBN, graphene HBN. And one indication of the good quality is the intensity of the 2D band with the G band, which would be, I mean, more than here we obtained around 8, which gives like very good quality. On the top here, I show some figures. Here you have the graphene flake. This is the dimension of the graphene flake, 20 by 30 microns, the bottom HBN and the top HBN. And then mixing all three, we obtain here our flake, our structure HBN, graphene, HBN. Okay, so then the next step is to develop like this asymmetric dual grating gate graphene field effect transistor, which mainly, so we have our flake, you can see the bottom HBN, graphene, and top HBN. So we are etching to make 1D contacts for the source and for the drain, and then making some e-beam lithography to make these fingers gate 2, gate 1, and on. Okay, so this is, in this case, we fabricate this asymmetric dual grating gate with these dimensions, where the dimension of the gate 1 is about 500 nanometer, the gate 2 is about 1 microns, and the distance between gate 1 and gate 2 is 1.5, and the other side from gate 2 to gate 1 is about 3 microns. Okay, so next we fabricate our device, which start for their characterization, electrical characterization, as well as the optical excitation. Here I show the case of the first device, device 1 with bilayer graphene. So you can see this is the grating. You have here the contact, the source contact, and the drain contact. This is the Dirac point measurement, the resistance of the channel versus the back gate. I forgot to mention this. I mean, we are using here the doped silicon as the back gate, and also the top two gates, gate 1 and gate 2. And from this measurement, we could extract the mobility, which is in the case at 4 Kelvin, it was about 37,000, which is not as good as expected. But nevertheless, we could observe some detection at low temperature. Here you can see the detection at 4.7 Kelvin up to 170 Kelvin. This is the case when we switch off and we switch on the terahertz beam. So this is the photocurrent that we are measuring at 4.7 Kelvin, about 40 picoamps, and also it goes down to 10 picoamps at 170 Kelvin, because I mean, you can see the Dirac point is not good and the mobility get decreased. So this was our first trial. Then we make another device, in this case with monolayer graphene, 4 grating for gate 1 and 3 grating for the gate 2. You can see here can see at 300 Kelvin, we obtained about at room temperature mobility of about 30,000. But at 4 Kelvin, we are having a mobility record like 250,000 centimeters square per volt seconds. And you can see here the Dirac point. So this is the photocurrents measured as function of the backgate. And you can see that we could reach an intensity of 1.5, around 1.5 nanoamps of currents at 4 Kelvin. Under excitation of 0.3 terahertz. But under excitation of 0.15 terahertz, I mean, the response was very low because the grating, the dimension are well fitted with the 0.3 terahertz than 0.15 terahertz. Because here, I mean, the simulation shows that the coupling with this dimension is good for 0.3 terahertz than 4.15 terahertz. And then here, the same measurement, when we switch on and switch off the light, you can see that the measurement is much more clear with a lot of less noisy from 4.7 Kelvin up to 250 Kelvin, which we should show here. It's about 100 picoamps at room temperature. Okay. And at room temperature, I just show here some video. I hope it works. So mainly here you have you can see this is the parabolic mirror. The device is around here. And this is the cable connection, electrical connection to locking amplifier, what we are seeing in this screen. The terahertz beam is coming to this direction, reflected with this parabolic mirror, go inside, reflected here, and then go to the device. Okay. So now we have the real signal in real time. And you can see when we put some metallic barrier, then the signal goes to 0. When we remove it, then we come back to its level. Okay. So next, what we have done is to put some materials like papers. I'll just go to. Okay, you can see if we put paper, part of the radiation is getting transmitted. So you can see that it's not going to 0, but it's going to lower because the paper have like some content of water and could absorb some part of the terahertz. So this is like a real demonstration of the detection at room temperature. So from this measurement, we extract the responsivity as well as the noise equivalent power, where we show that we obtained 85 microamps per watt and 1.39 watt per square root of hertz for the case of the noise equivalent power. Okay, so let me show that is very recent result that is still unpublished. In this case, we fabricate another device 3, with very much more high quality than the both other two devices with more fingers, as you can see here. And what we are showing in this case, the photo response as function of both top gates 1 and top gate 2. So the back gate was fixed around the Dirac point, and then we only changed the value of the both gates. And you can see that for specific places or specific conditions, we have the maximum signal, especially here. And in this place, you can see that the top gates have positive value, which is P-type, and top gates 2 have negative value, which is N-type. So when we have like this NP type region, as I mentioned here, the N-type means that we have conduction with electrons. P-type will have conduction of holes. So this is the behavior of the energy. So when we have this periodic structure, we observe a higher signal. Also, when we make the inverse, when we have PN region. But when we have PP or NN region, both are the same, then the signal is not, well, it's not as high as this. It's almost 0 because it's the white color. This is the measurement at 77 Kelvin, and this is the measurement close to room temperature, 200 Kelvin. So similar behavior has been observed. So we can play, the idea is we can play with these both gates to make it more, less, and also to change the responsivity and the noise equivalent power of this device. So finally, we use this the device 2 for the imaging. In this case, this is the terahertz sources. Going to the chopper because we have to modulate the beam for the lock-in technique measurement. They go in through different mirrors or parabolic mirrors. Here we are going to place our hidden object inside like paper or other packaging material, and then we make the detection with our transistors. Okay. So this is the terahertz source. This is like photo of the system. And you can see in this case, we place like a cutter, and this is the image we are obtaining from this type of measurement. Okay, in conclusion, we fabricate this structure based on these 2D materials, graphene encapsulated between 2 layers of HBN. This enhances the carrier mobility and the quality of the stack, and mainly also because we are not, I mean, the graphene sheet is not getting contaminated by other material. We make the terahertz characterization from Kelvin up to room temperature. We obtain these values of responsivity and noise equivalent power, and also we demonstrate the inspection of hidden object using the ADGG GFET mono layers. I would like to thank finally, I hope I didn't, okay. To thank my colleagues from Salamanca University, Dr. Juan Delgado Notario, who was in charge of the fabrication process, and other professors, for Jesus Enrique Velasquez and Enrique Diaz, and also our laboratory technician, Vito Clery. This work is done in collaboration with Professor Taishi Utsuji at the Research Institute of Electrical Communication at Tokyo University in Japan, and also with both Professor Taniguchi and Professor Watanabe from the National Institute of Material Science. Mainly they provide for us very high quality HBN material. Thanks for your attention. For more, for more detailed information, you can look for this publication, recent publication in 2020. Thanks for your attention.
Thank you very much, Dr. Meziani, for the very interesting lecture about your work.
And I believe there's already one question from anonymous attendee who said they are interested in this. I guess they were talking about Professor Meziani's presentation for energy efficient windows, and they think it will be a great invention for our life. So I see that Avnish has a question. I will allow to talk, so you should be able to unmute yourself, Avnish, and ask your question.
You know, I like the topic of graphene, and then in combination with HBN, of course, both the properties of both could be combined together and for good application as well. But then, what about the other two-dimensional material? For example, the competitor of graphene, such as phosphorine. I mean, phosphorine is, as compared to graphene, has more, let's say, the larger band gap and also bio compatible. So, what Professor, I think, Xiao would think about using graphene for the same application?
Yes. So your question is, there is another type of 2D materials, black phosphorus, right? Which has a direct band gap, right?
Yeah, exactly. And it's also biocompatible.
Yeah.
Yeah.
Of course, it's really depend on your applications, right? If you want to make some modulator devices, you need to tune kind of Fermi level of 2D materials. For this black phosphorus, it has a band gap, as it's difficult to tune. No, the graphene, because it's a semiconductor metal, it has Dirac point, it shows some unique properties for modulating application.
But the band gap of phosphorin is directly dependent on the layer, actually, the number of the layers.
Yes.
So,
Yeah.
I think it can be tuned, I guess, right? Or I'm wrong. I think it can be tuned, band gap of phosphorin.
Well, yeah, I cannot hear you very clearly.
Okay.
Sorry.
So, you know what I was saying, that the band gap of phosphorin is directly dependent on the number of the layers.
Yes.
So
Yes.
yeah, so I think it can be tuned, can be
No.
modulated, right?
Yeah, well, when I see tuning, it's kind of whether you can apply some voltage or chemical doping, right? Of course, this black phosphorus, the band gap is thickness dependent, right? But I'm not sure it can be, you know, tuned by electro bias. I don't think so.
Yeah. Actually, you know, I'm not a physicist. I'm a chemist.
Yeah.
So what I'm saying currently is trying to combine the phosphorin with some other conducting organic molecules to tune the gap, actually. Let's say for some electrocatalytic properties of phosphorin.
Yeah.
So, you know, and then I was interested in the physics. So you have explained much better, but with regard to graphene. And then the question arose in my mind, then how I can combine it with the phosphorin. Because phosphorin is, I think it's a competitor of graphene right now. Of course, it's not stable in air, but it's a competitor. Yeah.
Yeah, I think definitely we can explore this black phosphorus for some applications, right? Definitely, it's interesting because it has a direct band gap, right?
Yeah. Okay. Thank you. Thank you.
Sorry, if I can add something, just for the phosphorus. I mean, black phosphorus was already used for terahertz detection.
Oh, great.
And yes,
okay.
yeah, and there is some publication from people in Italy, I think. They already developed something, but most problematic, yeah, is competitor for, of course, a competitor of graphene. Whatever material, I mean, we show some good quality, it will be competitor. But in my understanding that the phosphorus is more unstable.
Yeah,
and
in air.
I mean, handling phosphorus is not as easy as handling the graphene. I think this is the weak point of the phosphorus, or the black phosphorus at least.
But we can stabilize it, you know, as a chemist, you know, I have found some way to stabilize it with some organic conducting moieties. That problem is also, I mean, it can be addressed. Yeah, nowadays.
Yeah.
Yeah. Thank you very much, by the way.
Thanks.
We have a few more questions in the Q&A box. One anonymous attendee. Hello, I have a question for Dr. Sanshui Xiao. Firstly, thank you for your presentation. And then for the 2D device, the structure is important for them. And most of them is sandwich structure. Why we choose sandwich structure? And I am wondering whether we can try to make it with other structures.
Okay, I think in the device that we demonstrate, actually, we don't protect graphene by use of HBN. So here, actually, yeah, we do have this kind of a graphene, aluminum oxide, graphene kind of, you can consider this is a sandwich, but this is just, we want to build like a capacitor between the graphene and dielectric material. Therefore, we are able to tune the Fermi level. That's the purpose of this kind of configurations. Actually, we don't use this HBN as a protection. Of course, you can use it. In our devices, we don't use a protection because graphene are kind of stable, right? Of course, if you want to improve the performance, it might to have the HBN incorporated. Yeah.
Okay, thank you. And then one last question for Dr. Meziani. Thank you for your presentation as well. And then the question is, I found you chose the HBN and GAAs, comparing with the metal semiconductor materials. What are the advantages of non-metal semiconductor materials?
Okay, thanks for the question. I mean, we are using HBN mainly for, I mean, to protect the graphene and also to use it as the dielectric for implementation of the top gates. Okay, so this is the part, this one part. And the gallium arsenide, I mean, gallium arsenide, yes, I mean, it was used for semiconductor, was used for, I mean, development of terahertz detectors, I mean, a few years ago, and it shows very good quality. But I mean, the idea now to use the graphene because it shows high mobility than gallium arsenide at room temperature. And also it's challenging to make the fabrication and to fabricate the device. But gallium arsenide, I mean, you can find devices. Yeah, it's already technology that is already manufactured. It's already known very well and controlled. So the idea now is to use this new type of material to make something new, and also to, if it is possible, to make in terms of detection, to make resonant detection, or to increase the responsivity in comparison with the gallium arsenide. So this is mainly why we are choosing this type of material. I hope this is this answer to your question.
Okay, thank you very much. I don't see any more questions. So I kind of hand back the microphone to Elias, and who can close the webinar.
Yes, Sarah, thanks. I think that we may close now the webinar if we don't have any other questions. I want to thank, really, I want to thank our invited speakers for very nice lectures. They had, according to our journal webinar. I want to thank also the organizers, that very good organization of this webinar, and I'm hoping that we have the opportunity just to repeat it with another topic in near future. Thank you very much, Charlotte, for very nice handling the situation with the webinar. And of course, our colleagues in China that also not appear now, but they had in mind very good organization. We have very good contact on this. Thank you again all, just to be here and listen to our invited speakers. Hoping to see you soon. So I want to say hello and wish you all the best for and keep safe. Thank you very much.
Thank you everyone for joining.
Thank you very much.
Have
Thank
a
you.
lovely day.
Bye.
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 Bye.